So, in last class we are discussing about the superposition of waves. So, we have seen that depending on the wavelength, frequency, amplitude and direction of the light, if we consider two waves, depending on their direction of the motion. So, there are three phenomena observed. One is interference, second is standing wave and third is beats. Okay. So, then we will continue the discussion on the interference. So, yes, in last class we have seen that this two wave y 1 and y 2, now due to superposition of these two wave. So, this displacement y as a function of x t comes like this. So, this is a travelling wave basically, but its amplitude depends on the phase difference of the two waves. So, square of this amplitude is basically the intensity of light. Okay. So, intensity of light depends on the cos square phi. Phi is the phase difference between the two waves at the point where they are interfering, they are meeting with each other. Okay. And this phi has to be constant for all time. It has to be constant for all time at that meeting point. Okay. So, if you plot phi as a function of this intensity as a function of phi, so we will get this type of variation of the intensity. So, basically bright, dark, this kind of contrast we will see, and that is called basically interference fringe. So, this interference fringe, whatever you are seeing, that depends on the basically phase difference between the two waves at the point where they are interfering. Okay. So, bright, dark, that contrast we are getting. So, their intensity is basically 4 times of maximum intensity, 4 times of square of amplitude, and this dark there it is 0. Okay. So, if this amplitude of these both waves are equal, so then contrast is better, means we take highest intensity as well as lowest intensity, that is 0. If A and A is not same, amplitude is not same for both, say it is A 1 and A 2. So, then it will be basically this bright one, it will be basically A 1 plus A 2 whole square, and this 4 times it will be there will be some other parts, of course, A 1 plus A 2 whole square, this maximum intensity, and A minus A 1 minus B 1 square, that will be the minimum intensity. So, if you take equal, so contrast will be better, otherwise contrast will be poor if the difference of A 1 and A 2 is large. So, minimum will not be if difference is large, that means this A1 minus A2 that will be large. So, you will not get basically 0 intensity, it will not looks like dark, only you will see some weak intensity and higher intensity. So, contrast will not be better. So, that is we tell in terms of visibility. So, visibility will not be better. So, for better visibility, if these amplitudes are equal, so that is the best. Okay. So, so from two source, two waves are coming, and from two source, one wave is this, another wave is this. So, these two will interfere at this point. So, path difference or phase difference between these two is basically for one case it is phi 1, whatever at the source it was there, and for another case its initial phase was phi 2. So, phi 2 plus this path difference. So, this is the normal. So, this side path are same, additional path travelled by this wave is S to p. So, corresponding phase difference 2 pi by lambda is to p. So, so this phase difference phi is phi 2 plus 2 pi by lambda is to p minus phi 1. So, condition for bright and dark was this cos square phi equal to 0. So, that is the condition for dark. So, when we will get 0? When phi is 2n plus 1 pi by 2. Okay. And so, this is the condition we will get dark if phase difference between these two waves at the interfering point or at the point where they are meeting, superposition of these two waves at this point. So, depending on their phase difference, if phase difference is this, then we will get dark. If phase difference is this, phi equal to n pi, okay. So, we will get bright, we will get bright fringe. Okay. So, this for both cases, this is basically n equal to 0, 1, plus minus 1, plus minus 2, etc. Okay. So, since it is square is there, so minus value also square of it, it will be plus. So, what is S to P, how to calculate? So, that if this angle is from this is the normal distance between the source and screen, if it is capital D, and the source distance is small d, and that their meeting point is at from the center it is a x distance, if it makes angle theta. So, this will be also theta, this normal, and here this is normal on this. So, these two angle will be same. So, if angle is small, so we can write sin theta equal to s to p by d equal to tan theta, that is x by capital D. Okay. From there s to p equal to x d by d. So, path difference is basically the distance of the point where we are observing the path difference or phase difference or interference effect. So, if that distance is x, so x into source distance between two source divided by d, capital D, that is the distance between the source and screen. Okay. So, this is very common relation for this type of all experiment. Basically, this relation is valid. whenever two sources are there, their distance is known, distance of the skin from the source is known, then basically that x will vary at different points. What will be the phase difference? Depending on that, we will see bright dark this type of fringe, that is basically interference fringe. So, in this relation here, this phase difference. So, there is to p that actually we found it is this. So, this can be replaced here, this can be replaced here, and then basically in terms of this parameter x small d capital D, we will get the phase difference. Okay. So, condition for dark and bright fringe. So, at x, if it is nth number of fringe, okay. So, for nth bright fringe, so x we are writing x n d by d, that the path difference. Okay. So, we are assuming say phi 1 equal to phi 2 equal to 0, okay, or may not be 0, but this initially at the source the initial phase are equal. So, phi 1 minus phi 2 is basically then 0. So, only in that term there will be path difference s to p and phase difference 2 pi by lambda s to p. So, now then we can write that this path difference will depend on, for a particular source and skin distance, this x n. So, nth this is a general term x n, nth bright fringe. So, n minus 1, n minus 2, n minus 3, etc. You can get from this relation. So, that will be when it is nth. So, path difference will be n lambda. Okay. So, for n plus 1 bright fringe, so it will be at distance x n plus 1. So, when their path difference will be n plus 1 lambda. Okay. So, then distance between these two n plus 1 and nth bright fringe. So, distance between these two is basically the width of the bright fringe. So, if it is beta, so beta will be equal to from here you can find out d capital D by small d into lambda. Okay. So, this is the fringe width. Similarly, for dark fringe, so this relation is 2n plus 1 lambda by 2 or n plus half lambda. Okay. So, for nth dark fringe, so this difference nth bright fringe and nth dark fringe. So, this the path difference will be lambda by 2. Okay. So, you will get nth bright fringe is this is the path difference, and n plus 1th dark fringe for this n equal to n plus 1, if we put this will be the path difference. So, width of this dark fringe will be capital D by small d lambda. So, from here you can tell, you can see that the fringe width, okay, in general we can tell it can be difference between two successive bright fringe, or it can be difference between two successive dark fringe. Okay. So, that means width between dark and bright fringe will be half of it, Okay. So, for interference fringe, the width of bright fringe and dark fringe is all the time same. So, and this is the condition, we have to remember this fringe width basically capital D by small d into lambda. So, from here basically what is the wavelength if you want to find out. So, it small d by capital D into fringe width. Okay. So, so now here one term I use that these two source has to be coherent. These two source has to be coherent. Okay. So, their phase difference will remain constant over the time. Okay. So, let us discuss this very important fact for seeing the interference effect. The source, the two source we are using, that has to be coherent. So, mandatory or compulsory requirement for the for observing interference fringe is the two or more coherent source which have single frequency and constant phase difference. Okay. So, two or more coherent sources, and those coherent source should have single frequency and constant phase difference. Okay. So, it is just like this, these two waves, okay, their wavelength are same, frequency are same. So, in this case the initial phase difference is basically 0, and other case you can see. Okay. So, here this its amplitude is minimum 0 and here amplitude is maximum. Okay. So, this basically one case is sine function, another is cos function. Okay. So, initial phase between these two is the is pi by 2. Okay. So, this initial phase difference has to be constant in general wherever also at the meeting point where they will interfere, at that point also total phase difference including the initial phase difference has to be constant with time. Okay. So, then we tell the source are coherent. Additional requirement, source must emit light in the same state of polarization. This is the additional requirement. So, if lights are polarized, so the source must emit light in the same state of polarization, sigma polarization, pi polarization. So, these two will not interfere. Okay. So, interference will happen only between pi pi or between sigma sigma. Okay. And amplitude must be nearly equal, as I told, may not be equal, but it's it should be nearly equal. So, these are additional condition to see the better visibility of the interference pattern. So, for observing the interference phenomena, coherence of light is must. So, two independent source. So, how to get two coherent source? Okay. How to get two coherent source? That is the question. So, two independent, if you take two independent source of light, they never be coherent. Okay. So, the coherent source of light can be obtained either by the source and obtaining its virtual image, or by obtaining two virtual image of the same source. Okay. So, we have to basically we cannot take two different source, we have to from same source we have to uh, generate another source. Okay. So, that we tell there is a image of the source, virtual image of the source. Okay. Either original source and another is its virtual image of that source. So, these two can be coherent, or from the original source if we generate two virtual source and that two virtual source we are taking as a for our experiment, okay, for observing the interference effect. So, then these two virtual sources are also coherent. Okay. So, this is because any change of phase in real source will cause a simultaneous and equal change in its image. Okay. So, that is why from same source we have to generate another source, or we have to generate two more source from the same source, then they will be coherent. Okay. So, generally coherence in interference is obtained by two methods, okay, from same source. Okay. We can get the two or more coherent source by two method. So, that is one is division of wavefront and another is division of amplitude. So, wavefront you know, so this is the spherical wavefront. Okay. So, now here if we have two pinhole, okay, this wavefront is falling on this screen where two pinholes are there. So, this from each pinhole again. So, these wavefronts are dividing into two part. Okay. So, one part is entering this way, another is entering this way. Okay. So, this is a division of wavefront, and division of amplitude is basically so this is the source light is coming. So, here basically you have a beam splitter or half silver glass plate. Okay. So, it can reflect as well as it can refract. So, from this glass plate one part is reflected and another part is transmitted. Okay. So, basically we are generating two part. Okay. So, these two can be used for interference. So, basically we are generating two waves by this method. So, basically this method is based on the division of amplitude. So, whatever amplitude there, it is divided into two parts. So, this is called division of amplitude. Okay. So, now important fact is that this to get the coherent source, we are using as I mentioned that two methods, either division of wavefront or division of amplitude. Okay. So, it's and we are telling that this phase difference should be independent of time between these two waves which will interfere. Okay. So, now coherent slightly difficult subject, and let me slightly discuss more about the coherent. So, there are two types of coherent. This is called temporal coherent and spatial coherence. Okay. So, so what is this two types of coherence? So, this for getting the interference effect. So, we are telling that source has to be coherent. means, or the two waves which will interfere at some point. So, there at that point their path difference or phase difference has to be independent of time. Okay. So, that is the condition for to be coherent. Now, this condition remain the phase constant, phase difference constant. So, to get this condition, there are other factors are there, okay, or how we can maintain this condition. So, to understand or to realize that one, so that we express in terms of these two types of coherence, one is temporal, another spatial. So, ideal concept that phase difference between two sources remain constant not only at source position for all time, but at distance of screen where waves from the two sources interfere for all time. Okay. So, these phase difference constant not only at the source level, source position, but it has to be at the at a point on screen at any distance, okay, for all the time. Okay. So, so reality is that no light. So, before that let me tell you that light waves. So, to achieve this one, basically condition is that light wave has to be strictly monochromatic, and the phase wavefront is which one, what is wavefront? Wavefront is basically the phase on a surface, is uniform, is constant. Okay. So, then that surface is called the wavefront. Okay. So, this is the definition of wavefront, and if it is strictly uniform, as well as we tell this for interference we need monochromatic light, okay, means for a particular wavelength. So, you can see for one wavelength will not interfere with the another wavelength, okay, because as you told, this interference only possible of same frequency and wavelength. Okay. So, if you have two source, their frequency or wavelengths are different. So, then there will not be interference. So, that is clear, but if you take source of wavelength lambda, so no source basically have this single wavelength lambda, always every source have a natural width, bandwidth. Okay. So, whatever the definition we give for monochromatic light, definition we give for wavefront, if that is strictly followed, then there is no, then this phase difference will remain constant at any time, at any distance. Okay. So, but in reality it is not possible, it is not possible. What is not possible? To get strictly monochromatic light, whatever light we will use, so that has bandwidth. So, bandwidth may be very is very small, but still it will be there. So, no light wave is strictly monochromatic it has a frequency width. Also, phase at a different points on a wavefront is not strictly uniform, it varies. Okay. So, this is the ideal concept of monochromatic light and a uniform wavefront. Okay. So, phase will remain constant at all points on a wavefront. So, these are ideal concept, but in reality we deviate from this concept, we deviate from this ideal concept. So, that means we are admitting that, so whatever light we will use, it will have bandwidth, it is not single frequency, single wavelength, as well as whatever light will emit wavefront. So, those wavefronts is not perfectly uniform, means their phase on the wavefronts are not same at everywhere. So, it will vary. So, it is a defect from ideal concept, it is deviate, there is a defect on that ideal concept. Okay. So, whatever the condition we are telling for getting coherent source, so there is a limitation on that. Okay. For any time it will not happen, for any distance it will not happen. Okay. So, there is a limitation on it. So, that is what this temporal coherence and spatial coherence, these two terms has come up. So, we will discuss more on this issue. So, what is temporal coherence? It tells about the degree of perfectness of monochromatic light, as I discussed. So, other way, if phi, what is phi? So, this is the wave trend, this is the wave. Okay. So, if you take 2 points A and B in the direction of propagation on the wave. Okay. So, if phase at point A, it is phi A, and point B, it is phi B. So, phase difference between these 2 points A and B is phi A minus phi B. Okay. If phi is independent of time, then point A and point B are said to exhibit temporal coherence or longitudinal coherence. So, what is temporal coherence? So, between 2 points on the wave at the direction of propagation, if their phase difference remain constant, if it is independent of time, then we tell that the source is temporarily coherent. Okay. If it varies, then it is not, it is incoherent. So, this is the example of incoherence. Okay. It varies along the with time, it varies, is a time axis. Okay. So, with time it varies, it varies, phase varies at different points. Okay. So, or at a particular point, say A or B. So, with time it is varying like this. Okay. So, then we tell with time the phase at a point or difference between 2 points will not remain constant. So, this source So, this source is not coherent because it, so which type, so that now we classify why it is not coherent, because time part, in time part it is incoherent. So, that is we are telling temporal temporal coherence or temporal incoherence. Okay. So, if so, if time with time it varies at a particular point, if it varies like this, so it is all the time, it is fine. Okay. Periodically it will come. So, phase difference between 2 points will remain constant with time. So, then we tell this temporal coherent. Okay. So, this different way people tell about the, to understand that coherence, temporal coherence. So, this is one way, okay, to understand the temporal coherence, and the similar way the spatial coherence, it tells about the degree of uniformity of phase on a wavefront. Okay. So, this is the wavefront, plane wavefront is not spherical wavefront, plane wavefront. Okay. So, now spatial coherence we on a plane, on a wavefront, on a wavefront. So, if we take 2 point A and B, and if their phase difference remain constant with time, then we tell them that they are spatially coherent, they are spatially coherent. Okay. So, if this phi is independent of time, if this phi is independent of time, then it is said to exhibit spatial coherent or transverse coherence or lateral coherence. So, from this discussion it is clear that when the wave is travelling in this direction. Okay. So, in transverse direction, if we take 2 point, if we take 2 point, it can be on same, it can be on same wavefront, or it can be on different. No, it has to be on same wavefront. So, in case of spherical, that means we have to take point will not be on the same perpendicular line, but it will be A here and another B here, okay, on spherical surface. Okay. So, phase should be same, supposed to be same at this both point. If it is not same, okay, if there is a difference, and if difference remain constant over the time, then we tell them it can be 0 or it can have some value. So, if it is independent of time all the time, then we tell this source is spatially coherent. Okay. So, this is the example of spatial coherent is the spherical, or this is the example of and but if it is like this. Okay. So, if you take 2 points on a wavefront, so this phase is not uniform. Okay. So, then we tell this spatially incoherent. To observe the interference, okay, source has to be coherent, means source has to be temporarily coherent as well as spatially coherent. Okay. So, it has to satisfy both condition. So, if I discuss slightly more, so this way also we can understand this. This is a wavefront, plane wavefront we have taken. So, here if you it is propagating this direction, so is a time axis as well as propagation this as well as space axis, okay, z as well as time. Okay. So, over time if we look at 2 point, okay, along this direction. So, you can see this they will remain constant, it is propagating. So, they will remain constant, okay. Their phase will remain constant, and over in transverse direction also if you consider 2 points, So their phase uniform on this wavefront. Okay. So this type of source wavefront, okay, waves, we tell spatial and temporal coherence. If it is like this, okay, so its vertical direction, this phase is changing with time, okay, but along this direction, okay, so you can see this their distance. So it is a moving, okay. So phase difference between these in longitudinal direction, so it will remain constant. So this type of source we can tell this is a temporal coherence, but spatial incoherence. Another next one, it is showing that this phase in uniform in longitudinal direction, transverse direction, but in this direction they are not like this, okay. So phase difference between 2 points at the direction of propagation, so it will not remain constant, okay. So this we tell this is spatial coherent, but temporal incoherent. And then just in both way, there is a phase difference along the transverse direction as well as along the longitudinal direction, okay, direction of propagation. So then we tell this source is spatial and temporal incoherent, okay. So this way we try to understand. So so basically one can measure the temporal coherence time or temporal coherence length, okay. What is temporal coherence time and temporal coherence length? Actually if source is not strictly monochromatic, if it has bandwidth, okay, if delta nu, okay, bandwidth, so then it's actually we do not get wave, long wave, we get basically wave in packet form, okay. It is like pulse form, okay. So so this coherent time that depends on the bandwidth of this light. So it is the inversely proportional, okay. So coherent time will be infinity if this delta nu is 0, okay. So if there is no bandwidth, so up to, so all the time it will be coherent. So its a time is infinity. If it is higher, this value is higher, then this time coherent time will be lower. And over the length with velocity c, if it moves, so over the length LC equal to basically c tau c coherent time. So this is called basically coherent length. So over this length it is temporal coherent along the direction of propagation, okay. So if this type of arrangement is there, so where path difference between two light which will interfere, I will discuss more about this. This is basically Michelson interferometer geometry. I will discuss more about this. So if you change the distance d, initial for 0 distance, so you will get nice fringe pattern. Now you are changing the distance, and after when d will be very large, then you will see this, it will vanish, okay. So what is that distance after which it vanish? So that generally we tell the temporal coherent length, and if you know the temporal coherent length, you can find out the temporal coherent time, okay. So and For longitudinal, these the longitudinals. For transverse or spatial coherent. So, if your source dimension size is bigger, if it is point source, so it will be spatially coherent, but if size is increased, okay, so there is a critical size. After that you will lose the interference fringe pattern, okay, it will vanish. So, if point source, if really point source, then it will be spatially coherent, it will be spatially coherent. Now, if source size is d, is not source separation, source size is d. So, there will be many point source on this. So, from middle, so this light is coming, okay, from middle, from that source, point source. So, you will get a interference pattern, okay. So, bright one you will get at the center, okay, bright one you will get at the center, okay, and if you take green one here, black line, and if you take another point source at the extreme end, 2 point source at the extreme to end. So, their fringe pattern you will get like this from this, because this will be center of the fringe. So, you will get this type. So, what you are seeing this at as if the is the broadening of the interference fringe, and then there will be overlapping of minimum of another one with the maximum of other one, okay, as if this is happening due to the many point source, means due to the larger size of the point source. So, we will lose the coherence. So, coherent, spatial coherent basically depends on this size of the source, as well as it depends distance between these two sources. If it is smaller, then better. So, there are some factors, but size of the source is important fact, okay. So, here whatever the source, here two source, if their size, if it is not pinhole, if its size is bigger, so you lose the visibility of the interference effect. So, the size generally is depends on size as well as depends on distance of the skin also. So, it is not unique relation, but some theorem tells that critical area over which this will get spatial coherence. So, that is that equal to it depends on this relation is d square lambda square divided by pi small d square. So, here it is clear that this if this size of the source is smaller, so this area will be higher, means over the higher area we will get the it will remain the spatial coherent, and if distance from the source is higher, then also area will be the spatial coherent area will be higher, okay. So, so skin distance is higher is better, higher wavelength also it is better for spatial coherent, and smaller source size is better for spatial coherent, okay. So, so that means whatever coherent we are talking about, so we have to be careful that it has to be spatially coherent as well as it has to be temporal coherent. So, both condition has to satisfy, okay. So, I will stop here. Thank you for your attention.